All right, welcome back. Today I'm going to talk about galaxy evolution, basically looking at old light of galaxies and comparing it to young light of galaxies to kind of put together a timeline, if you will, of how galaxies do form. So we'll talk about the lives of galaxies and then end with a unique kind of feature called quasars and other active galactic nuclei. Ooh, say that 5 times. So again, we're looking at observations from very distant galaxies and kind of comparing them to younger galaxies to kind of fill in the pieces as to what stages are these galaxies in. So in our previous lecture, we talked about there are 3 types of galaxies, elliptical galaxies, spiral galaxy, and irregular galaxies. And again, we're looking at old light, distant light, to kind of look at young galaxies and figure out what makes them, take the shape that they are in. So, studying galaxy formation, we can't really observe the earliest galaxies, but I did come across an article put out by CNN, and I'm sure if you just Google farthest galaxy ever seen, an article will pop up about it. So it's just kind of recent news within the last couple of years. But our best models for galaxy formation, we assume that matter filled all space almost uniformly, so you can kind of see that spread out real nice, and then gravity kind of pulled it towards the center over time, and then we get something called a protogalactic cloud, very similar to our protostar clouds. It's not a true star because fusion hasn't taken place yet. Well, protogalactic means like before it turns into a galaxy. And so we have hydrogen and helium as our first gases in these clouds. Maybe supernova explosions from the first stars kept much of the gas from forming stars, and any leftover settled due to conservation of angular momentum, which is something that we've mentioned a lot in this semester. So the lives of galaxies. Why do galaxies differ? Why do we get spiral galaxies or elliptical or irregular? Well, a lot of it has to do with maybe density of the protogalactic clouds. So maybe density. Elliptical galaxies come from very dense protogalactic clouds that might have been able to cool and form stars before gas settled into a disk to get the spiral. Spin could also play a role in determining what kind of galaxy that protogalactic cloud will be. So the initial angular momentum could determine the size of the resultant disk. But again, when we look at very distant red elliptical galaxies, it supports the idea that most of their stars formed early in the history of the universe because they are red and kind of towards the end of their life stages. With galaxies, we do observe galaxies colliding with other galaxies. And so we think that collisions were a lot more common in earlier universe time because they were closer together. But a lot of the galaxies you see at great distances, and again, great distances means we're looking at early in time, you can see that they are violently disturbed. So it says in this diagram here, this collision between 2 spiral galaxies stripped out 2 tidal tails of stars, 1 and 2, and triggered a burst of star formation, producing many young blue star clusters. And then this is just showing age in the universe 2 to 4 billion years versus 5 to 7. So, we do see some observations, but we use a lot of modeling to show how 2 spiral galaxies can merge and make an elliptical, so they can actually morph in from one type to another. Shells of stars observed around some elliptical galaxies are probably the remains of past collisions. And then obviously looking at these collisions, we can explain why elliptical galaxies, remember, are really, really close together in clusters versus spiral, where they were just in groups of a few dozen. Giant elliptical galaxies at the centers of clusters seem to have consumed a number of smaller galaxies. So yeah, they kind of swallow, one galaxy can kind of swallow another. Okay, some galaxies are considered starburst galaxies, which means that their star formation is so fast, they use up all of their gas in less than 1 billion years. And it's just, if you just look at this diagram right here, you can see a lot of blue light, which just means a lot of hot stars burning through their fuels. Sorry, I have my son with me here. Going through their hydrogen and helium at a faster rate than normal. Yeah, I know. Okay, so starburst galaxies, we've been, sorry, I just lost my train of thought. So anyways, there are a small percentage of galaxies that are forming stars at a very, very exponential rate. So we call them starburst galaxies. And they're kind of a stage of evolution that many galaxies might have gone through at least once during their lives. This is a very temporary stage in a galaxy's life because the rates of the star formation it's very unsustainable. So like, for example, the Milky Way galaxy produces an average about one new star per year. And at this rate, our galaxy won't exhaust the interstellar gas in its disk until after our sun has died. In contrast, these starburst galaxies form new stars at rates exceeding 100 stars per year, which means that more than 100 times the star formation rate of the Milky Way galaxy. It means that they're going to consume all of their interstellar gas in just a few 100 million years. So, yeah. So anyways, galactic winds, supernova explosions can drive away most of the gas. Okay, the final thing I want to talk about are quasars and then active galactic nuclei. So quasar stands for quasi-stellar radio source, and they were first detected back in the 1960s. They are star-like emitters of radio waves. So we detected their radio waves in the 1960s. And we found that this very distant object is powered by black holes 1 billion times. In a book I was reading, it said 26 quadrillion, I don't know, some outrageous number as massive as our sun. And we recently just found one only 13 billion light years away. These quasars do give off a lot of energy, more than 100 normal galaxies, and they can be 1 trillion times brighter than the sun. And so they think that all of this energy output, this light that we see, the energy we detect, is produced from massive black holes that lie in the center of which that quasar is located. So if the center of a galaxy is unusually bright, we call it an active galactic nucleus. And using redshift, kind of Doppler-like data, these quasars do indicate that they are really, really, really far away. So from brightness and distance, we can figure out maybe some luminosities of these quasars and how great they are versus our sun. And they think that galaxies that are found around quasars appear disturbed by collisions. So maybe collision resulted in it. But yeah, these quasars do emit a lot of energy in a wide range of wavelengths. So you can kind of see that they give off gamma rays and X-rays and ultraviolet and visible light, infrared, and then radio waves. So radio galaxies contain active nuclei, and they can also shoot out jets of plasma that also emits radio waves. And so we call this an active galactic nucleus, and how it shoots out plasma almost at the speed of light. So because, again, of this large amount of energy being shot out, it suggests that there is a black hole near that quasar. So characteristics of active galaxies. Luminosities are great. They can rapidly vary. Okay, they emit energy over a wide range of wavelengths, and again, some of them can shoot out jets of plasma at near the speed of light. So my final question is, do supermassive black holes really exist? And every time I say supermassive black holes, I think of a song called Supermassive Black Hole. But anyways, orbits of stars at the center of the Milky Way indicate a black hole with the mass of 4 million masses of our suns. A lot of nearby galaxies, perhaps all of them, probably have supermassive black holes at their centers. These black holes seem to be dormant, active galactic nuclei, and it might have suggested they passed it through a quasar-like stage earlier in their time. Now, I just screenshotted something on Facebook as I was scrolling through this morning. Let me just read to you the headline that I came across. Hold on, buddy. Oh, please tell me I screenshotted it. I thought I did. There was an article about black holes, and one that we just found that kind of like verified. Shoots, I did not screenshot it. Can't believe I didn't. But it was talking about supermassive black holes. And I think my phone's listening to me, so it's posting these articles as I lecture to you. So, but anyways, that does it for galaxy evolution. We only have like 3 more chapters left. So we're actually going to be done with content by next Friday, like way before next Friday. And then I think we're going to watch Interstellar. But I'm having troubles because it's not on Netflix, and so I think I just might zoom it over in like 30-minute increments, but we'll see. I'm not exactly sure how I'm going to do this yet. But stay tuned.